A very important concept is the cumulative distribution function. Okay, whenever we're talking about random variables, maybe discrete, like this chapter, and later we're going to move to continuous random variables, the CDF, cumulative distribution function, is key in understanding many of the concepts here. So let's start with the definition. Okay, for a random variable x, the function f defined by, okay, so let's take a time to understand this expression a little bit more. Okay, so based on the definition, we know that this capital F x is called the cumulative distribution function, or the CDF of x. Okay, so that's the definition here. Okay, notice that the random variable is capital X. Okay, we have a small x over here, which is actually just any value on the real line. Okay, it is not a random variable. Okay, the small x is not a random variable, only the capital X is a random variable. Okay, so here the small x is just a value on the real line. So if you look at the right hand side, well, this definition of the CDF is telling us that the CDF of a random variable x, okay, to evaluate any value of small x, it is the same of thinking about the probability that the random variable capital X is smaller or equal to small x. Okay, so this sounds a little bit vague, like, again, maybe not as intuitive as we hope it could be, but let's go through some examples and some illustrations to make sure that we understand what the CDF is about, okay? And I'll also just lastly mention before we go to those examples is that notice the name of the CDF, it's cumulative, okay? So cumulative, and then you can see that we're sort of like thinking about the probability of x, capital X, going up to small x, small or equal to, okay? Small or equal to small x, okay? So what this is telling us is that it's cumulative. Okay, we're sort of like adding up all of the possible, like the probability of all of the possible values of x, capital X, up to smaller x. Okay, so that's what we mean by cumulative. Okay, we're really just looking at a distribution function cumulatively. And let's look at some properties and examples. Okay, capital X, okay, we always use that as a random variable, or capital Y, things like that. So always is the capital. Okay, the little x, the small x here, is a real valued number on the real line, just like what we highlighted over here. Okay, and smaller equal to is smaller equal to, okay, in the math notation. So let's think about our previous example earlier. Okay, so remember when we have a coin that we're flipping with probability P of getting a head, and we are thinking about the random variable as the number of flips that we need to have on until we have a first head. Okay, so remember we talked about this, right? If we're listing it out, we know that the first one will have to be a tail, the second one is a head, and then we have a generic expression of x equals to n, okay, which is 1 minus p, okay, to the power of n minus 1, because the first n minus 1 flips will have to be a tail, and then the last one is a head. Okay, all right, so, and then we said that, well, it can actually keep going on because, well, it doesn't have to be n ending at n. Okay, so let's put this into our CDF definition. Okay, so if we look at CDF, okay, if we're looking at the CDF of the same random variable for that experiment that we talked about in the previous video, then what this is telling us is that if I want to find the CDF, capital F, okay, of the random variable capital X at a particular value n, okay, then what this is telling us, if I'm following strictly of this definition here, I'm trying to figure out the probability of capital X is smaller or equal to n. Okay? And if I put it in this way, hopefully it starts to click, okay? This is essentially saying that we're adding up the probability of all of the possible values of the capital letter X, the random variable, okay, up to small n. Okay, so by definition, we are trying to get the probability of capital X is smaller or equal to small n. And then we know that, well, this particular random variable could take value 1, 2, up to n, and then keep going as well. If we stop at n, we're essentially adding them up. And I will also just highlight that we're adding them up because they're all disjoint, okay? They cannot happen at the same time, but they all satisfy this definition of x is smaller or equal to n. So we're adding it up, okay? And that's the third axiom of probability. Okay, if you have disjoint events, you are adding them up if you're trying to get the union. Alrighty, so let's see if we can simplify this a little bit more. Okay, so this is essentially saying that we're adding up all of those terms together. Okay, and one way to write it, if you think about it, is that if I am able to write 1 minus p times I minus 1, okay, with p, okay, let's just say that I, the little I over here, that's the number of flips that I have to make, okay? So I goes from 1 to small n, okay? So let's just check. When I equals to 1, it goes to this term, okay? When I equals to 2, it returns to this. When I equals to n, it returns to the last term, okay? So this, for now, I'm sure, well, I'll be happy if you stop here, but you can also notice from the knowledge and experience from Calc 2, which is 127, series and sequence from Vassar, or you have taken it in AP Stats at BC, you will notice that, well, we're looking at series here, okay? Because this is the probability, 1 minus p. So p is the probability between 0 and 1, so 1 minus p is also a probability between 0 and 1. Okay, so there, because we're doing a finite series over here, okay? So one way to simplify this further is that this will be 1 minus p to the power of n, because we're adding up to n terms, okay? And then divided by 1 minus p, okay? So this whole thing multiplied by p, okay? If we do a little bit more simplification, this will become this expression, okay? So in fact, even though we started off with something not like with the, definitely with the pattern, we know that the distribution associated probability with each of the possible outcomes has a certain pattern. And if we define this further in more detail, we're able to come to this particular example of showing the CDF of this particular example. Okay, so hopefully this gives you a understanding or opportunity to understand what we mean by the cumulative distribution function. And in practice, it is adding up the probability of the outcome variable, the random variables, the outcome of the random variables up to a certain point, okay? And that certain point is a real value, okay? It's on the real line. In the definition, we're using x to represent it, okay? But then in a lot of cases, you can use any other things that make sense to you, okay? But the key is the random variable, we always use capital letter, and then the lowercase, maybe small x, maybe any other value, like a letter, that could be, that should be used as a real value number instead of the random variable, just to avoid confusion.